Okay. All right. Hello, everyone. Welcome to the PC seminar. Today we have with us William Lochet from University of Bergen, and he'll be talking about exploiting dense structures in parameterized complexity. So thank you so much for joining us, William. Over to you now.
Thank you. So today we're going to talk about exploring dense structures in parameterized complexity, and most of the time it means dense graph. And this is joint work with Daniel Oktanov, Saket Sorav, and Mirav Sehavi from University of California, Institute of Mathematical Science in India, of course, and Bergen University in Israel. I read the chat, so you can ask a question on the chat, but you can also stop me on any point during this talk, and it's fine. Okay, so don't hesitate if there is something which is not very clear or anything. Just stop. Okay, so dense structures in parameterized complexity. Actually, what we want to study is dense graph. So in particular, we say that the graph G is alpha dense if every vertex of G has degree alpha times n. Okay, and n is the number of vertices. So the graph that we're looking at are graph with minimum linear minimum degree. Okay, so this is okay. So why are we interested in this class? The thing is that this class has a very long history of approximation algorithm on alpha dense graph. And especially, so people have been studying this class most of the time for cut problems, such as bisection, k-way cut, and other things like that. So there is a very long list of results, a very long list of successful results, and it started with Aura et al. In 1995, and I think they got like a best Fox paper award, I think, at that time. Okay, so it's quite an old topic, and with very nice results. And what happened is that not only they're able to obtain very nice results on alpha dense graph, but also what they developed is some very nice techniques and very nice ideas with a lot of application to related field or even like a bit different type of. So the first thing is, so Godrash et al. In 1998, they realized that these results, basically, or these ideas, has a very nice application to some property testing results. So in 2003, Allen et al. Showed that all of these results about p-tasses on, let's say, max cut, for example, they can be generalized to p-tasses for dense CSPs, which is also quite nice. And also, if you want to study decorrelation clustering, so you have an integer t, and then you have a graph j, and the question is, how many edges do I need to change? I mean, so remove or add for that, so that the graph becomes a union of d clicks. So this is a problem that we call decorrelation clustering. And if you want to solve this, I mean, if you want to find a p-task for this, then you need to use ideas that comes from this study of approximation algorithm alpha dense graph. Okay, and here it works on any graph, not just alpha dense, but any graph. Okay, so and here you have like two separate results. So first, theoretician Guru 20, and then a very a much better algorithm by Carpesian in 2000. Okay. So this is a nice class because when we study it, you find some nice ideas and some nice properties. And so the goal of this paper was really to try to look at this class of graph from the point of view of parameterized complexity. Because despite the fact that it has a very long history in approximation algorithm, we don't know much about what happens for parameterized questions. So in particular, what we study here today. So we do two things. There is really like two separate blocks in this paper, and we talk about both here. So the first block is to show that on this class of graph, we can obtain sub-exponential algorithm for a lot of nice problems that in general do not admit sub-exponential algorithm. So namely, what we show is sub-exponential algorithm for edge-out cyclotransversal, D-way cut, and minimum bisection. We also show linear kernels for these problems. And finally, we also obtain linear kernels for multi-cut and multi-way cut. Okay, so all of these results, I put them together because they use sort of the same ideas, and they basically based on sampling ideas that were developed before for these approximation algorithms. So basically, what we show is how to try to manipulate these ideas to get some nice FP2 result, basically. So this is one block, and we'll focus on edge-out cyclotransversal. And then there is another thing which is a bit separate, but it's on the same class of graph, is using a much more, let's say, structural approach and not much sampling. We can show that edge disjoint paths and vertex disjoint paths admit kernels on this class of graph. Okay, so linear kernel for efficient and then cubic kernel for not efficient. Okay, and then we'll see also basically what happened for edges. All right, so that's the goal. Try to understand this class and see what type of arguments has been used or we can use to develop some nice FPT results. All right, so let me start with edge odd cycle transversal. So what's the problem? The problem is you have a graph G and an edge K, and the question is, can you remove K edges so that the graph becomes bipartite? And S is the set of edges that you remove. So in general, this is FPT. This is just iterative compression technique. You have no sub-exponential algorithm under the ETH in general graph. This is no result. And what we show is that, okay, if you restrict yourself to this class of dense graphs, so minimum linear degree, linear minimum degree, sorry, then you can find a big O square root K algorithm. Okay, so sub-exponential. All right, so how do we do this? Well, first of all, let us change a bit the optic. Is that suppose that S is your solution. So to the way we presented here, the goal is to find a set of edges S of size K, so that when you remove your bipartite. But actually, if you look at S is the solution, and then when you remove S, you have a bipartite graph. So what we're most interested in is the bipartition, okay, more than the set of edges. I mean, it's just a flip of point of view. But if you have the bipartition, then the set of edges is just the edges inside, okay? So instead of looking for a set of edges to remove so that the bipartition, so that the graph is bipartite, what we're looking for is a bipartition which minimizes the edges inside. Okay, so it's just a different point of view, but it's actually much more common for us. And in particular, we can say something which is very important now, is that if AB is the optimal partition, so the partition that you obtain when you remove the minimum number of edges, then every point X in A must be such that the degree in B is larger than the degree in A, right? Because basically you have to remove all of the edges which are adjacent to X and a point in A. Okay, and so if this is more, then you just can just flip it, right? It's classical max code result, basically. So this is nice, and basically what it told us is that the whole goal of this algorithm is to try to understand where a point stands. So is it in A or is it in B? And to understand that, the only thing you need to know is, okay, is it degree larger in A or in B? Okay, so intuitively, the only thing we're trying to understand here is what's the degree of a point, I mean, of all the points inside A and inside B. And if you know this, then you know on which side they must belong. Okay, that's really the very broad approach, let's say. So how do we do this estimate? Well, basically, we will use some sort of sampling argument to estimate the degree inside A and B. And here there's one quick remark that we have to do is that suppose you have a point X, which is such that the degree of X in A is roughly equal to the degree of X in B. Okay, so it is half of its neighbors in both sides. Okay, well, intuitively, these points, they are troublesome for us because we're trying to estimate the degree and say, okay, it must belong to A or it must belong to B. But if the degree is roughly the same, then you need to be very precise in order to be able to tell if this point belongs to A and B. Okay, so that's a bad thing, and we have to control this guy. And intuitively, what happens is that if a point is like this, okay, then you know that you have to remove half of its of the edges adjacent to it in the solution. And so we will use this in order to control the number of such points. Okay. All right. So more precisely, the first thing we need to say is that we can always assume that K is small compared to n squared. Okay. So let's say alpha n over 200 squared. And the reason for that is that there is a very easy 2 to the n algorithm for this problem, because whenever you have a bipartition, you know exactly what is the cost of this bipartition, right? It's just the number of edges inside. So if you try all the bipartition and then count for each the number of edges which are inside, you can obtain the best possible solution, okay? And this gives you just 2 to the n. All right. So now, if K is larger than, let's say, alpha n over 200 squared, then basically it means that n is a little over square root K. Okay, so K is like a big O of, K is a big O of n squared, so n is a big O of square root K. So it means that 2 to the n, it's exactly 2 to the square root K, right? So if K is too big compared to n squared, then just the trivial algorithm works. Okay. So what it means for us is that for now on, we can always assume that k is small. Okay, so that's the good point. So from now on, suppose that S is the optimal solution, so the minimum number of edges to remove, and then AB is the corresponding partition. So the first thing we show is that if you denote by L, the set of vertices adjacent to more than alpha over n, alpha times n divided by 200 vertices, edges, okay? So adjacent to more than a constant fraction of the edges, then we have that L is smaller than alpha n over 100. Okay, so L is small. And why is that? Is that if you do L times square root k, because every point in L is adjacent to at least square root k edges. If you do L times square root k divided by 2, you have a lower bound on the number of edges inside S, and so this has to be smaller than k, okay, because S is psi k. All right, and so now a quick computation tells you that L is over the square root k. Ah, nice. Okay, so remember why do I do this? It's because yeah, I can say it later. So this is the picture. This is the picture. I'm going to be clear. So you have AB, which is the optimal partition, which is the partition we're trying to figure out. And then you have these vertices, which is L, which is small. But these are the bad vertices, meaning that they are the vertices which are adjacent to a lot of edges of the solution. Okay? And a lot is not so much, right? It's just alpha n over 200, but it's still too much for us. And for the other, which is almost all of the graph, I mean 99% of the graph, the vertices, they're adjacent to very few edges in the solution. Okay, so if you note A1 and B1, so the A minus L and B minus L, what's very interesting for us is that if X belongs to A1, then it means that its degree in A is less than alpha n over 200, right? Because you have to remove all the edges between X and the other vertices in A. So because this point is adjacent to less than alpha n over 200 edges of the solution, it means that its degree in A is very small. I mean, alpha n over 200, and its degree in B is alpha n minus, okay, 1 minus 1 over 200. So basically for this point, its degree in A is like 200 times smaller than its degree in B. So intuitively, then this point, I mean, intuitively, this is very nice because if you get an estimation of the degree of this point, then you will know, okay, if it has to belong in B and A, okay? So that's really the intuition. So L, it's a small number of vertices, alpha n over 100, for which it would be hard for us to guess where they belong to because, okay, the solution changed too much the degree of size of this point inside both parts. Okay, but for the rest, the difference in degree in both sides is sufficiently large so that you can basically get the idea. All right, so now the question that you're asking is, how do we get an estimate of the degree inside both parts? Okay, and here comes the very nice sampling ideas, and this idea has been studied, I mean, it's been used since 1995, basically, probably before, so it's quite a long, it's quite a very useful lemma, but it has been used for a long time, and it's basically the core of, let's say, all of these split tests. So suppose you have n1, which is the size of A, okay, this, and now suppose that you do a sampling of t vertices in A, okay. So for the moment, I mean, suppose you know A, we get to that part. Suppose you know A, and you're trying to estimate the degree of some of the points in A by sampling in A. So you sample m points, so you sample t points, and this is your set M, uniformly at random in A. Okay, you suppose it's a multi-set, so you can pick the same point twice. This doesn't really matter. And now you look at the random variable. So you fix a vertex X in the graph, and then you look at the random variable, the neighborhood of X intersection M. So what is the size of the intersection of the neighborhood of X with this set M? So how many points in M is adjacent to X? Okay, so this is a random variable. And this random variable follows a very known distribution, which is the binomial distribution, right? Because every time you pick one vertex, what is the probability that this vertex is adjacent to X? Well, it's just the size of the neighborhood of X in A divided by the total size of X, right? You pick uniformly at random inside A, so this is clear. And then you do T draw. Okay, so this random variables, follows a binomial distribution with parameters this and this. And in particular, the expected value of okay, M intersection N of X is exactly T times D of A X divided by 1. Okay, just like T times the parameter. This is the standard thing. Um, and this is very nice because remember, this is what we're trying to estimate, which is the degree of X in A. And so if you take this random variable and then you multiply it by N1 divided by T, the expected value of this is your degree. Okay, so you're quite happy about it. And now basically you use standard bound. So let's say Chebyshev. Okay, so to bound the deviation of this variable. So using Chebyshev, what you can show is that for any vertex, the probability that so this value differs from the expected value by, let's say, epsilon times t is smaller than 1 over epsilon squared t. Okay, just apply the classical Chebyshev stuff, and you know that the variance of the binomial distribution is smaller than t, basically. And so basically what it means that if you pick t large enough, and here large enough is just compared to epsilon, okay, not compared to the size n1, but just compared to epsilon, then what you can have is that, so what I said before, so n1 times, okay, the intersection divided by t is roughly equal to the degree of X in A plus minus epsilon n1, okay? And n1 would be, let's say, A and B have the same size, so it would be n over 2, okay? So by doing this, and so you know that this is true with very large probability. I mean, it just depends on t and the probability that you want, but yeah, that's possible. So by picking a constant number of vertices, you can make a mistakes of epsilon n with probability less, at least 1 minus epsilon. Okay, so here there is two things. First of all, you see why it's very interesting for us for the degree to be large, I mean linear, because like this mistakes is very small, but it's only very small because this is linear. Okay, so if your degree is a constant and you make this mistake, then I mean, it doesn't tell you anything. Okay, and so basically, yeah. And here, what's very important is that t only depends on epsilon and not on n. So it's really a constant number of points that you have to sample. Okay, so we've used Chebyshev, and now we use the second thing, which is very famous for, I mean, all of these applications, very powerful too, is, okay, now you can use Markov, okay? So if you use Markov, basically what you can show is that if you pick the right number of vertices, and here it only depends on, let's say, alpha, okay, then with constant probability, you will have that this value, okay, is equal to, okay, the degree of X in A plus or minus alpha n over 200. Okay, and this is true, and this is why you use Markov for all but alpha n over 200 points. Okay, so again, for some constants which only depend on alpha, basically what you will have is for 99% of the points, you will get the good estimate of the degree in A with precision 99%. Okay, right. 99 is just constant each time, but yeah, this is the whole idea. So sampling a constant number of points in A gives you a very nice thing. And here, this is very nice. And then, so let me remind you why we defined the set L before, is that if a point belongs to L, it means, remember what we said, L is like, it means that this point, if a point does not belong to L, it means that this point is adjacent to less than alpha n over 200 vertices to the solution. And in particular, it means that the degree of X in A is less than alpha n over 200. Okay. So now suppose that you guess properly the degree of X in A, I mean, using this formula. So you have a mistake of alpha n over 200, but basically what it means that your estimate tells you that the degree of this point in A is alpha n over 100. Okay. So it tells you, okay, you see alpha n over 100 in A, and then alpha n, and then let's say alpha n in B. Okay. So the difference is too big. So basically, you know that you have to put this point in A. Okay, so that's really the good thing about L and this estimate is that, okay, you can make a very, I mean, you can make a constant size mistakes, which is alpha n over 200, but still you will have a good idea of what this point needs to be, right? So that's the first remark. And then obviously the question now is, okay, this is very nice, but for this you need to sample in A, but you don't know A. Okay, so what do you do? I mean, you need to sample in A in order to guess A. So there is one more trick that you need to do. And here the very interesting thing is that because you only need a constant number of vertices, basically what you can do is the following. So for the moment, suppose that N1, which is the size of A, is larger than the size of B. Okay, So it means that n1 is like n over 2, or at least n over 2. And now if you pick uniformly at random in G, so in your whole graph, so now you don't need to know what is A, what is B, um, for every point that you select, because A is the largest of these two sets, with probability 1/2 you're in A, and so with probability 1/2 of the T, I mean 1/2 to the T, the full set is in A. Okay, and if you condition by this fact, then the distribution that you get is exactly what you had before. So suppose that this is true. So this is true with constant probability, right? Because we said that T only depends on alpha and not on n. Okay, so with constant probability, you know that M is included in A. And if it's the case, then with constant probability, this value here is a good estimate of the degree of almost every point. Okay, so that's the trick. And this is why it's important that you select only a constant number of points. It's because then like you have constant probability to always hit A when you just sample uniformly at random in the graph. Okay, so that's the good part of it. And now let us call X the set of points for which this isn't a good estimate. So as I said before, this makes a mistake for a tiny portion of the vertices, and this is what we call X, and X is smaller than alpha n over 200. Okay, so for the moment, okay, so now suppose that M has been picked successfully. We know that we have constant probability that this happens, so now just assume it happens. And the interesting is, so X union L is small. And what I mean by small is alpha n over 50. So remember, L are the points for which it would be hard to decide if they belong to A and B because their degree inside both parts might be too big. And X is the set of points for which the estimate that you get by taking this value is bad. Okay. And so these 2 points, they're basically the troublesome, the trouble points for us, but you don't have too many of them. That's the first thing. Okay, so now that we have our estimate of the degree, let us partition us according to this estimate. So in particular, let B prime be the set of vertices so that the estimate tells you that the degree in A is more than half of the degree of X plus alpha n over 25. Okay, so the estimate tells you, okay, you see really more points in A than you see in B. So basically what we say, okay, in that case, then you have to be in B. And then the lemma is that if X is a point in B, which is not in X union L, okay, so not on, I mean, so it means that, okay, you see way more points in A than in B, and moreover, the estimate is a good estimate, then you have to belong to B prime, and this is not very hard. Okay, let's just go through it. But if you don't belong to L, it means that the degree in A is larger than the degree of X minus alpha n over 200, okay? And if you don't belong to X, then it means that this value here is at least the degree in A minus alpha n over 200, right, which is the mistake you're allowed to make. And then finally, you put them together, and then you get that this is at least the degree of X minus alpha n over 100. And because the degree of X is larger than alpha n over 2, alpha n, you get that this is larger than the degree of X over 2 plus alpha n over 25. Okay, it's not very hard. Everything is just we chose this one. So that's a good thing. So if you're in B and you're not in X and not in L, then you will belong to B prime. And then you can show, which is basically exactly the same thing, that if you're in A and you're not in X, so meaning that this estimate is not too bad, then you will never be in B prime. Okay. And the reason for that is that if you're in A, it means that your degree in B is larger than the degree in A. Okay. So you see less than the half of the degree dx over 2 in A. So in order for this estimate to give you this, it means you have to make a mistake of at least alpha n over 25. And if you make a mistake of alpha n over 25 in your estimate, then it means you belong to X. Okay, just by definition. Okay. All right. So this is how you guess B. We do exactly the same thing for how to guess A prime. So if this estimate tells you that you see way less than half of the points, and here way less is alpha n over 25, then you have to belong to A. Okay, and again, if you're point in A and you don't belong to X union L, then you have to be in A prime. And if you're a point in B and you don't belong to X, then you will never belong to A prime. So what I mean is that the vertices that you place wrongly belong to X union L. Okay, so here, when I do this, I don't place all the vertices. Okay, because I mean, some of the vertices you will have that the estimate tells you it's half. Okay, and in that case, you cannot say, okay, either in A or B, so you don't say anything. But you will guess some of it. And what's really interesting is that if you look at the points which are not placed, okay, and the points which are placed but wrongly placed, then this has size at most this, which is, I said, alpha over 100, that's alpha n over 50. But it's small. Let's just say it's small. Okay, so that's the picture. So you have A prime, B prime, and then you have the rest that you don't know how to deal with. And now what happened is that if you look at the rest and the points which are not, I mean, nicely placed, I mean, which are not correctly placed, let's say, then this is correct up to alpha n over 100. So apart from these red points, which are bad, okay, so they're not placed or wrongly placed, everything is almost good, right? And now the question is, okay, so you know that when you do this partition, you made a very small number of mistakes. I mean, very small. Still linear, but small, let's say, compared to alpha n. But the question is, okay, but you don't know. I mean, how do you guess which are the mistakes? How do you know which points you made wrong? And here, this is where the whole tricks appear, is that basically you will use this first estimate of the partition in order to get a refined view on the degree. Okay. So what I mean by that, if you look at the intersection for every point x, it's very important that's every point. The intersection of the neighborhood of x in B prime, it's basically the intersection of, I mean, of the neighborhood of x in B minus the points which are wrongly placed, right? I mean, this is fine. But you know that the points that were wrongly placed, this is at most alpha n over 100. So it means that when you take these value, it's roughly n of x intersection B plus minus alpha n over 100. Okay, so now if you take these value at the degree of x in B prime, okay, for every point x, this will be a good estimate up to alpha n over 100. Okay, so before we had, by doing this sampling, we had to accept that a certain number of points, the degree that this estimate gives you is wrong. Okay, but okay, it's a small portion. But now, if you take n of x intersection B prime as your degree in B, then for every point, this will be a good estimate. Okay, so that's the whole trick. So that's the whole trick. So and now we do exactly what we did before, meaning that we use this estimate to partition. Okay, but now that we're very happy that we don't make mistakes. I mean, for every point, the mistake that we have for this degree is very small. Okay, so now let SA, so the second guess for A, be the set of vertices X, so that the degree of X, I mean, this new estimate of the degree in B is at least half of the degree plus alpha n over 50. Okay, and SB is the same thing, but this is now the estimate in A prime. Okay. So we have our new estimate of the degree in A and B, and now if you tell me, okay, my degree in B should be way larger than half, okay, then you belong to A. And if you say, okay, my degree in A is should be way larger than half, then okay, you belong to B. Right? So that's the way we guess it. And now something very nice happens, is that this set is a subset of A. Okay. So SA, the new guess for A, it's a subset of A, and moreover, it contains all the points in A1. So remember that A1 was A minus L. So L was the points for which we couldn't decide, and we still cannot decide here. But apart from these points, we guess everybody else right, and this is very nice. Okay, and the same thing applies for B1, of course. And here again, it's the same proof as before. So if X belongs to A1, so meaning it doesn't belong to L, and it belongs to A. So the degree of X in B is at least the degree of X minus alpha n over 200. This is how we define that. And now when you take this, so your new estimate, it's at least this and minus a mistake. I mean, this is what we said, right? The mistake you make is at most this. So it's the degree of B in X, of X in B, sorry, minus this mistakes. But again, since the degree of X is at least alpha n, then you can get this. Okay, so this point, the estimate of the degree is like almost everything, and it gives you this. And so this is to show that the point in A1 has to be in SA. Okay, so this means that A1 is included in SA. And now let us show that SA contains only points in A. Okay, so if Y belongs to B, then you know that the degree of Y in B is less than half. Okay, this is the first remark that we did. Okay, and now that what it tells us is that this is less than, okay, half plus alpha n over 1 plus 1 alpha n over 100, right? Because this is a mistake of at most alpha n over 100, so this is fine. Okay, and now this is not big enough to be in A prime. Okay, so that's this is not big enough to be in SA. Okay. So A1 is contained in SA, and no points in B are contained in SA. So we have this inequality, and for B, it's SB, it's exactly symmetrical. All right, so this is the point. So again, here with this condition, you don't partition everything. I mean, you have some points for which this and this would be roughly equal, and for them, you don't know where they belong to. But what is very nice is that these points, they must belong to L. Okay, so this is the picture that you have. You have SA, SB, okay? And now you know that SA and B, you didn't make any mistakes here, meaning that every point in SA is in A and every point in SB is in B. And then you have the rest that you didn't partition yet. Okay, so here two things. First is that until now, everything we did is polynomial. I mean, you sample, you count the degree, it's very easy, and then you do a second round, you just count the degree again. Basically, you count the degree twice, so you can do it in like n squared. Okay, so this is everything that we did now is strictly polynomial, assuming that k is small, of course. So that's one thing. And the second thing we have to say is that, okay, now what do we know? What do we do with R? Okay, how do we deal with R? Okay, and here the nice thing is that R is a subset of L. Okay, and as we showed, L has size square root k. So I mean order of square root k. So basically now what we do with R is just we brute force again. You can try all the bipartition of R and then you assign it to either A or B. Okay, and this will cost you only 2 to the size of R, and this is 2 to the big O square root k. Okay, so we're not able to say anything smart about R, but since R is small, we can just go over it we can just brute force it and it will be fine. Okay, and so finally, what we did is that for any alpha, there exists a 2 to square root k over alpha algorithm, right? So that's the complete algorithm. That's it. And the very nice part is just, with the sampling, you get the first estimate of the degree, okay? And when you partition according to this first estimate, is give you another estimate of the degree, and this one is much better because basically you don't make any mistakes. Okay, so that's, yeah. Okay, yeah, okay, no, I have to say this. Okay, so now we can also show that if k is smaller than alpha n over 200, what we did before gives you a polynomial time algorithm to solve this problem. Why? Because, as I said before, everything we do until here is strictly polynomial. Okay, so the only thing that happened is that you have to guess what happened to R, and this would cost you like a sub-exponential time. But remember that R is contained in L, okay? And the way we define L is the set of points which are adjacent to more than alpha n over 200 edges. But if k is smaller than this, it means that L is empty, okay? I mean, okay, there is no point adjacent to more than alpha n over 200 edges because there is less than alpha n over 200 edges in the solution. So L is empty, so R is empty. Okay, and everything we did was polynomial time, so basically you have the full partition. That's it. Okay, so if k is basically linear, I mean small but still linear, then you can solve this in polynomial time. Okay, and what it means by that is that this gives you immediately a linear kernel on alpha d square for this problem, right? And the kernel is the following: is that if k is smaller than this, then solve the problem, and if k is larger than this, then it means that n is a big O of k. Okay, and so the linear kernel is just the full graph, right? So that's basically it. Okay, so that's how you get sub-exponential algorithm and linear kernel for this problem, okay, which is quite neat. So basically, this approach of like guessing basically twice, so first time with sampling and then the second time with a preliminary partition, let's say, it can be used for a lot of problems where estimating the degree of vertices instead a constant number of parts is required. Okay, so for example, minimum bisection, it's the same thing. What you want is you want to have to partition your graph in two so that so that you maximize the number of edges inside. So it's like the complementary. Okay, and now again, what I mean, in order to know if you're in A or in B, the only thing that matters is, okay, I mean, what's your degree? So this can be solved exactly the same, and you have also like multiple cut problems. So D-way cut, multi-way cut, and this type of things. And sometimes we're only able to do linear kernels. So what happens is that sometimes basically you're able to reach the point when you have this set R, I mean the rest, and then it's too hard. I mean, or we don't succeed to know what you do with R. Okay, so if that's the case, then we don't get the sub-exponential algorithm, but we still get the linear kernels. Okay, so that's nice. And that one quick remark is that all these algorithms can be de-randomized. Okay, and so this is also something new that we did in this paper. And in fact, we can also show that most of the p-tasks that they existed before can also be de-randomized. Okay, so you don't need to go over the sampling basically. And again, like it wasn't known for these p-tasks. So it's also a nice result. Okay, so that's basically half of the talk, and this is the half where I talk about these cut problems and this sub-exponential algorithm. So before going to H disjoint paths, I mean disjoint paths in general, is this clear, or do you have any questions? Because now we basically changed topics. It's a good time to ask. Okay, so I assume no questions, so let's go to the disjoint path problem. Okay, disjoint path. So what is a disjoint path problem? Okay, problem that you all know. So you have a graph G, a set of k pairs of vertices, S1, T1, Sk, Tk. And now the question is, can you find k disjoint paths so that every pi is a path between Si and Ti? So you want to link S1, T1, S2, T2, S3, T3. And usually here disjoint can be H disjoint or vertex disjoint. In general graph, it's mostly the same thing. So here, there's a very famous FPT algorithm. This is Robertson and Seymour using very advanced technique, let's say, which tells you that the problem is in N cube. And but we know that there is no polynomial kernel for this problem. Okay. So this is what happened in general graph. And now the question is what happened in alpha dense graph. And yes. And this is good. So the first thing that we need to say about, I mean, the first remark that we give for alpha dense graph is that the problem is still hard. Okay, so the problem is still hard on alpha dense graph. That's one thing. I mean, I didn't show previous time, but here the reduction is quite easy. And actually, it's still hard on the click. Okay, and the reduction is the following. Suppose you have your favorite. Oh yeah, and here I will only focus on edge disjoint. Okay, so edge disjoint is just mean that the paths that you need to take, they must be edge disjoint. Okay, so they can share vertices, but they cannot share edge. Okay. So how do you show that this is hard? Well, you take your favorite instance of the edge disjoint path in general graph. Okay, and now every time you have a non-edge, UV in your graph G, then you add the edge, of course, you want to click, and you add the request. Okay, so at the end, what you have is you have a click, okay, and then you have way too many requests, but still you have a edge disjoint path problem on the click, which is dense. So if the problem is polynomial, okay, and then here the remark is that whenever you have an edge disjoint path problem, and then you have a request UV, and in your graph there is the edge UV, then you can take it. It's fine. Nothing bad will happen to your problem. Okay, so there would always be a solution where every request where the edge exists, you take the edge. So what it means is that now if you find a solution in your click with this added constraint, then actually what you find is a solution to this. Okay, so that's it. So the problem is still NP-hard on the click. I mean, when you don't parameterize the number of paths. But what we can show is that if the number of requests is not too big, okay, and here it would be still linear but not too big, then the problem becomes polynomial, and this is what I will talk to you about in the remaining 20 minutes. Okay, so for every alpha, there will be a constant, C alpha, which is very small compared to alpha. This is, okay, here it means like, don't worry about the constant, just think of it as very small, but okay, still a constant. So that every edge disjoint path problem in alpha dense graph, where you have the number of requests k is smaller than alpha, C alpha times n, this can be solved in polynomial time. Okay, it doesn't depend on k. But okay, all right. So that's what we're trying to show today. And how do we? What are we doing in order to show this? Well, oh yeah, and the first remark is that as before, if you have a polynomial time algorithm where its k is linear, small but still linear, then it means that you have a linear grammar, right? The same trait. Okay, so that's fine. Okay, so how do we show? I mean, what are the tools that we use in order to show that the previous result? So we find a polynomial algorithm when k is not too big but still linear. So what we use is cuts, some cuts version, so some connectivity concept. There is a very old lemma by Huck which says that if your graph G is k plus 2 edge connected, then any k edge disjoint pass problem has a solution. So if your graph is well connected, then you will always have to say yes. You can always say yes. Okay. So what it means that basically the problem that you have is when your graph is not connected. Okay? So in particular, if you're trying to solve an instance of this k edge disjoint pass on G, then you always have like k cut. In your graph G. There will always be a k cut. I mean, there will be a k plus 2 cuts, but for the rest of the talk, I will drop the 2 just because it's way more convenient to say this. Okay, so suppose that Huck tells you that that's not true. Huh? This is tight actually. That if you k edge connected, then you have a solution to every k edge disjoint pass problem. Okay, just because I don't want to say k all the time. Okay, so if you're trying to solve an instance of the problem with k equal to Cn, let's say, and Cn is very small compared to alpha n, it means that your graph G will contain a cut, and this is the cut, and the cut has size at most C times n. Okay, and so what is very interesting about this cut? Okay, and because I mean C, we will be able to choose C to be very small. Basically, what we can do with this cut is we can densify the two part here. Okay, and this will be basically the main idea of this algorithm. So what do I mean by densify? So suppose you remove these edges, okay, and then you have two parts. Okay. The first thing to say is that every vertex has degree at least, okay, in its part, alpha minus C times n. I mean, because if you take a point here, then its degree is like here, or it's one of these edges, or you use these edges and you have less than Cn edges here. So the degree is alpha minus C times n. Okay, and here the intuition is that C is very small compared to alpha, so the degree is still alpha n. Let's say this. But now the interesting part is that because this point has degree, let's say alpha over 2, I mean alpha minus C times n, then it means that this has size at least, okay, alpha minus C times n, right? So in particular, these parts, because this part has size at least alpha minus Cn, this part has size at most 1 minus alpha plus Cn. Okay, I mean, this is alpha minus Cn, and so you remove at least this from this side. So, and here, this is at least, let's say, alpha over 2. Okay, so every part has size at most 1 minus alpha over 2 times n. So what is the intuition here? So by doing this cut and remove these edges, if C is very small compared to alpha, you lose every point, lose a bit of degree. Okay, let's say 1% or 1 million or something like that. But the good thing is that every part, I mean, now you have two parts, but the graph, I mean, the part that you're in, it's much smaller. I mean, here it's alpha, but okay, if alpha and C are comparable, you can see how you did. But so you lose a bit of degree, but your part becomes much smaller. So intuitively, you become denser in the sense that you see a larger proportion of the vertices of your part. Okay, and so this is the intuition. And now let me do a few computation. Suppose that C is smaller than this. Okay, so here, so 1 minus alpha over 2 is what is it? Yes. It's smaller than 1 minus alpha over 3. Okay, I mean you remove much more. You remove more. So this is smaller than this. So this is smaller than 1, and so this can be done. Okay, so you can choose C so that C is smaller than alpha times this. Okay, this is possible, and it's still a constant. And you start to see why I don't want to express. I mean to tell you exactly what C of alpha is. So if this is the case, then the degree of X in A, as we said, it's at least alpha n minus Cn, okay? And now if you use this bound on C, it gives that this degree is at least, so alpha n times 1 minus alpha over 2 divided by 1 minus alpha over 3. Okay, and now you do the little trick of basically putting this and this together. So it's at least, I mean, it's equal actually, alpha over 1 minus alpha over 3 times 1 minus alpha over 2n. Okay, but if you look at this, 1 minus alpha over 2n, this is an upper bound on the size of a. Okay, because each size has size at most this. Okay, so basically the degree of x in a is at least alpha divided by 1 minus alpha over 3 times a. Okay, so this is smaller than 1. So basically this is larger than alpha. Okay, so you started with every point has degree alpha n. Okay, so every point is alpha of the vertices. And now, after you're doing this cut, in each of the, I mean, in each part, every point sees a larger proportion of the vertices. Okay, and that's really the nice thing, because you're able to make it denser. Okay, so as long as there is a cut, a small cut, I mean, so as long as the connectivity is not large enough for us, then you will be able to make your graph denser. I mean, your part denser. Okay, so formally what happens? Suppose A now is not CN connected again. Okay, so A is not CN connected, so you can find a new cut, and then you have A1 and 2. Okay, and if you do the same argument as before, what you have is that now every point in A1 is such that the degree of x in A1 is at least, okay, alpha divided by 1 minus alpha over 3 squared, okay, times A1. Okay, so here it sees even more, I mean, a larger portion of its parts. And so if you cut t times, meaning so you cut, then there is a small, then the graph is not connected, so you cut again, etc., etc. So if you do it t times, then basically the degree, I mean, the denseness will be alpha divided by 1 minus alpha over 3 times t. Okay, so this is good. And the other remark is that if you do this, if you cut t times, then the degree of a point is larger than alpha minus t times c alpha times n. Okay, because I mean, you start with alpha n, and at each cut, because you cut with cn edges, then at each cut you lose cn, so you lose t times cn. Okay, but now if you look at this number, okay, so this is a constant. This is a constant which is strictly smaller than 1. So if you put it to the t, then you get you tend to 0. So basically what it means that you can find such a constant t which only depends on alpha. Okay, and this is very important. Okay, so that this number is greater than 2/3. Okay, so suppose you have alpha. Now you choose t like this. Okay, and now that you've choose t and you have alpha, you will choose c of alpha, so that alpha minus t times c of alpha is at least alpha over 2. Okay, this is always possible if c alpha is very small. Okay, so again, you see why I don't want to explicit c of alpha. And now what happened? Suppose you chose t and c alpha like this. Okay, and then you do this t times. So you cut t times, meaning at each time there is always a cn cut. Okay, and now you reach a part where, first of all, I mean, every point sees 2/3 of the vertices. Okay, so it's very hard. And moreover, every point has degree at least alpha n over 2. Okay, because this is just the way we chose c of alpha. So every point see 2/3 of vertices. The degree of each point is at least alpha n over 2, meaning there is at least alpha n over 2 points in this part. Okay, and now when you take 2 points, x and y, in this part, they have 1/3 of the vertices of the whole part in common. Okay, they all see 2/3 of it, so the intersection is at least 1/3. But basically, because this part has size at least alpha n over 2, it means that these 2 points, they share alpha n over 6 neighbors. All right, but now, if cn alpha is smaller than alpha n over 6, so again, you can choose it like this, then these 2 points are obviously cn alpha connected, right? I mean, if you have common neighbors of size k, then you have the k disjoint parts. They're very easy to find. Okay, so basically what I'm telling you is that by densifying and densifying and densifying, okay, in the finite number step, you can get to a point where the graph is so dense that everything has to be connected. Okay, so in other words, this trick of cutting every time you find a part which is not highly connected has to stop. Okay, and it has to stop at some depth, which is t, and t only depends on alpha. Okay, so that's the whole trick. Okay, because now basically what we can show, and what we just showed basically, is that for any alpha, you can find a constancy of alpha such that if J is an alpha dense graph on n vertices, then you have a partition of J into a constant number of parts, and actually you can choose this constant to be smaller than 2 over alpha. Okay, so these parts are V1, Vj, so that every part is C alpha n connected. Okay, and this is just what we did before. You just cut, cut, cut until you cannot. Okay, and once you cannot, you have exactly this. So the only thing you need to show is that you cut. I mean, you stop at some point. Okay, and then the stopping argument are just negative. So this is your graph. Okay, so this is the full graph. So every part here is C alpha n connected. Okay, and then you have some edges in between the parts. Okay, and basically the intuition is that, remember what we wanted to show, right? We wanted to solve edge disjoint path on this graph. Okay, with k pairs, k vertices, and k is smaller than alpha. And here, intuitively, what happened is that on every sub part, I mean, on every graph induced by these parts, you know that you're always connected enough so that you can always solve any k disjoint path problem. Okay, so that's basically every part would be very nice for our problem, and what we're trying to understand is the connectivity between these parts. Okay, so that would be very roughly what we're doing. So the first claim on how to use this partition to find an algorithm for this disjoint path problem is the following. If the problem has a solution, then there is one, so that the intersection of every path with a part is a subpath. Okay, so basically what it means that your solution that you're looking for, it will play very nicely with this partition, because basically what happens is, like, okay, you stay inside, then you change part, you stay inside, then you change part, then you stay inside, then you change part, and then you reach the final part. Okay, so that's basically what happens. Okay, so how you show this? It's not very hard. So suppose you have a solution, P1, Pk, and then suppose you have Vj, which is a part of the decomposition. Okay, and then now you suppose that, let's say k is equal to 2 now. The paths, they behave not very nicely with this part, meaning that, okay, so the parts, it start with from S1, you reach this point. So this point is the first intersection with this component. Then you stay a bit inside, then you go out, you go back inside, and then you continue, and then you go out, and then you do the same thing with green. Okay, so if this happens, then the intersection of, let's say, the orange part and this partition is not a subpath. It's like it's the union of these two paths. So this is bad. Okay, so what we want to say is that we can actually modify the solution so that this is not just a path. Okay, so what you do is you consider the first and last points of this intersection, of the intersection of the path and this path. So here, this is the first point, this is the last point, and this is the first point, and this is the last point. And so basically, these pairs, they define a new disjoint path problem on your subgraph G induced by Vj. Okay, and here, because you have a pair for each path, it's a disjoint path problem with just C alpha times n pairs. Okay, and this is the whole magic of it. You know that inside this this graph here, you can solve this problem, right? So there is a way to go from here to here, only using the edges inside this subgraph, and from here to here, only using these edges of this subgraph, so that they disjoint, right? Because this is well-connected part, and you know that if you're well-connected, you can find a solution. So basically, what we do is just we find a solution only using edges vertices and edges in this subgraph, and then we replace the original subpath from here to here by the new subpath. Okay, and what we claim is that now we still have a solution. Okay, so I mean, this was the first intersection between the orange and this thing. So this is a path from S1 to this graph, to this point, not using Vj. This is a path. Then you have a path from this point to T1, not using Vj. And so when you put this, you still have a path between S1 and T1. Okay, and here it's nice because now the intersection of this path with Vj is just this path, this subpath. So you have what you want. Okay. So they are paths, and they're obviously disjoint. I mean, they were disjoint before, disjoint after, and because the way we chose these things, the paths after this do not use Vj. Okay, so they won't intersect with the new subsection that we have. So everything is fine. So this is a good solution. I mean, this is still a solution. And now, when you look at the intersection of pi intersection Vj, then this is a subpath. Okay. So basically what happened is like, okay, so you clean your solution for Vj, and then you have to do this for every part, but it always worked. And a quick remark is that it's not very hard to see that when you fix what happened on Vj, you don't change anything what happened on the rest. Okay, so if it's good enough, all right. Okay, so now it's very nice. So basically the solution, I mean, the solution that you're looking for, it has a very nice intersection with this thing. Okay, and now what you do is you will contract all of these components, okay, all of these parts. So let G prime be the graph obtained by contracting each VI, okay, keeping multi-edges. And it's very important because these multi-edges, they will be where the difficulties of the problem come from. And now you also basically contract your problem. So you define a new k disjoint path problem on this graph by just taking as S1 prime the part, I mean the vertex corresponding to the part containing S1, and then T1 prime the vertex corresponding to the part containing T1. Okay, so basically what happened is that, so this is your first graph, and now you contract every one of these components to a single vertex. And now if you wanted to go from a vertex here to the vertex here, then now what you want is you want to go from this vertex to this vertex. Okay, so very easy. You just contract and then you remember where you wanted to go, but now you just basically what you remember is just from which part to which part you wanted to go. Okay, so that's the thing. And the first, and what we claim is that actually the two problems, so the one in G and the one in G prime, are equivalent. Okay, so that's and basically that's the whole proof. And so one side is very easy because you can always, if you have a solution, okay, in G, you can always assume that the intersection of the path of the solution and every part is a subpath. So when you contract, you still have a path. I mean, you don't go back and create some sort of loop, so everything is fine. Okay, so this is one side. And now the question is, how do you show that if you have a solution in G prime, then you have a solution in G? So what is a solution in G prime? Basically, it's, okay, so a path between S1 prime and T1 prime in G prime, basically it's a sequence of, it's a set of edges between the components, I mean, between the paths. And basically, it tells you how you can go from the first component to the last component, okay? So let's say this was S1, this is T1. So this component becomes S1 prime when you contract, and this component becomes T1 prime when you contract. And so a path from S1 prime to T1 prime is just like two edges, let's say. So one between this component, and one between this component, this component. Okay, and if you do the same thing between S2 and T2, okay, so you have some sort of edges between the components. And now the only thing you need to do is you sort of need to fill out so what happened inside each component. So here, for example, you need to go from here to here, okay, one part. And then here, you need to go from here to here and from here to here with this disjoint, and here from here to here, here to here. Okay, but on each part, basically you have one entry point and one exit point. Okay, so this defines you one pair. So for each path, you have one pair. So in total, you have a k disjoint path to solve inside each component, but you know that there is always a solution of the k disjoint path inside this component. So you can always fill out this path into a path from S1 to T1, and here a path between S2 and T2. Okay, so again, you use the fact that inside you can solve anything you want in order to lift up a solution in G prime to a solution in G. Okay, and now I'm almost done. I might skip the thing. So this is basically what I say. So on every Vj, the PIs, they define a k disjoint path problem, and then you can solve it, and then you can combine it to get the solution. And so now the question is, how do you solve the problem in G prime? Okay, and that's the only thing we have to do left. Solve the, I mean, find a solution in polynomial time to this problem in G prime. Okay, so now what we can show is that you can solve this problem in G prime in k to some constant times n to a big O of 1, where the constant is just 2 over alpha times 2 over alpha factorial. Okay, so how do we show this? Well, the thing that you have to remember is that G prime, the number of points in G prime is just the number of parts in your decomposition theorem. And we said that this is at most 2 over alpha. So G prime is a graph on 2 over alpha vertices. So you might have a lot of edges. Okay, so this is, I mean, you might have order of O edges. So you have some like order of n multi-edges between the parts. So, and these are very important to understand, but you have a finite number of points. I mean, it's basically 2. So in particular, what is a path in G prime? It's a sequence of vertices. Okay, so you don't see it as a sequence of edges because for these you have a lot of paths. But if you just look at it as a sequence of vertices, then I mean you have a finite number of vertices, so you have a finite number of paths. Okay, and here the way we count is just to say, okay, a path is a subset of vertices and a permutation. Okay, so the number of possible paths is 2 to the 2 over alpha, which is the number of subset of vertices, and okay, 2 over alpha, 2 divided by alpha factorial, it's just a permutation. Okay, so you have new path. All right, and now what is a solution? So there's a strange thing that happened here is that, so a solution to this problem is just you assign a path to a pair. Okay, so every pair you assign a path, but if you do this, you have new choices for each pair, and then since you have k pairs, it gives you new to the k, and k is over the n, so this is very bad. So the way we look at this is a solution. It's basically an assignment of, for every path, the number of requests it will solve. Okay, so you have a path between a vertex in G prime to another vertex in G prime. Okay, and then a solution is just telling you how many demands these paths will solve. Okay, so for every path you might have like several paths using the same sequence, right? If you have multi-edges, for example, you have many paths using the same sequence. But since we're looking at paths only as a set of vertices, okay, a solution to the problem is just an assignment of a number of requests to every path. Okay, so for every path you tell how many requests you're solving. And now if you do this, then the number of possible assignment is, for each path you have k choices, okay, because you have just k requests to solve, so it gives you k to the new. Okay, so this is fine. And now whenever you try an assignment, okay, basically you try all of them, the only thing you need to know to see if this is a good solution is that if an edge is not used too many times. Okay, so if an edge between 2 vertices in G prime is used less than its multiplicity, okay, then you know that your solution is actually, your assignment is actually a good solution. And this can be, I mean, you just have to count. So this is done in your time. Okay, so it's a strange thing, but you can just, I mean, yeah, just you have a finite number of paths, so you can just count the number of times each path is solved. And that's basically it. That's basically it. That's basically the full argument, which is nice. It's quite small. So again, this gives you polynomial time algorithm when k is small, I mean, but still over the n. Okay, so the reverse is that it's a linear curve. So now let me just, okay, I'm a bit overboard. 2 minutes on what happened for the vertex disjoint path problem. Okay, so for the vertex disjoint, so for the edge disjoint path problem, the core of the argument is that if you're k plus 2 edge connected, then you can solve any k edge disjoint path problem. So a similar argument exists in the vertex disjoint case. So this is Rodobas and Thomason. It's a much more difficult result. But basically, they show that if you're 22k vertex connected, then every instance of the k vertex disjoint path admits a solution in G. Okay. So again, if you're trying to find a solution, you still have a small vertex cut, okay, which is like this. But now the problem, if you're trying to densify, is that you don't know what to do with the points in the cut. Okay, so for example, this guy, okay, it sees, let's say it sees most of its vertices here, so you can put it here. But let's say you have a guy here, it sees half and half. Okay, so where do you put it when you want to partition? Okay, and this is where the whole problem comes from. And so basically what we're able to do is to find a decomposition which is similar. I mean, the argument is exactly the same. So as long as you can find a cut, you find a cut. But here, basically, there is one part in your decomposition, which is the bin, basically. So there is one part which consists of all the vertex cut, And for this part, you don't have any control on its connectivity. So the solution, the decomposition is just a constant number of parts. There's V0 for which you don't know anything apart from the fact that it's small. It will be small compared to our file. And then all of the rest is connected. And basically that's that's the main problem. So now the question is, how do you deal with this? It's much more complicated. So in particular, but you still have some nice properties. So yeah, and that's anything I want to say about it. You can read the paper on my website if you want, but it gets very technical. So yeah, just a warning. And so finally, just the conclusion. So we've seen two different things, but I think there are two nice arguments. So I want to tell you both of them. The first thing is how to get sub-exponential algorithm on CAD programs. So sampling to get a first estimate of the degree. Using this estimate, you make a first partition which is bad but not too bad. And using this partition, you get a better estimate, which allows you to basically finish. And then also how to do kernels for edge disjoint paths in alpha dense graph. Use cut to densify. And then once you have some dense parts, then basically they're all connected and you can solve the problem. Okay, and that's it. Now I thank you, and then I listen to all the questions that you might like to ask.
Thank you so much for the talk. And yes, we are open for questions now. If you have any questions, just unmute and ask. Or if you prefer, you can type in the chat.
I guess that's it.
What would you, I guess, I'd like to say, what would you want to say about like future work?
So, yes, there might be some open question here, like for these two. So for the moment, we just have linear kernel, and then we don't know if there is a sub-exponential algorithm. So, but we don't have lower bounds. I mean, we don't have any reason to think that it's not possible. So it might be possible, it might not be. I mean, these are hard problems, so I'm not entirely sure if it's true. But yeah, I guess that's the obvious question is to push this to get sub-exponential algorithm. For the disjoint paths, I doubt this can be improved. But
okay,
yeah, that's just a thing.
Right. Okay, then I suppose there are no other questions. So I'd like to thank you once again for the talk. It was great to have you. And thanks to the audience for being around. We conclude our session for today here. So see you all next week. Thank you. Bye.